So, ladies and gentlemen, before we hand over, I'm going to take you onto a couple of arrangements for asking the questions. So you'll see on the right-hand side there is a little question box. What we ask you to do is to put your questions in there. You may put your questions in there as the speakers go through the slides. We will pick them up, and at the end of the session I will ask those questions. As I say, I may combine questions for time efficiency. If questions don't come to you, you can ask questions as we get into the question and answer session. And I'd certainly encourage you to do so, because we all get much more out of these sessions when we get lots of questions. We can't always answer all of the questions in the time, but I'm delighted to say that we're very happy in the Institute to follow up with the questions, and all of this material will be on the website in a couple of days' time, including a recording of this if somebody isn't able to benefit from going through it today. So it's a very simple process, and as I say, we're delighted to have your questions, because that makes for a good session. So with that, I'm going to hand over to Hette and to Andy to start the presentation.
So it's Andy Reid here, and I'm pleased to be introducing the talk and introducing Hette Hylkema. It's a Dutch name, you get used to it, but he's been looking after the interfaces between the capture plant and MPP3 right from the beginning of the project, and he will take you through the technical details for the presentation. My job is just to give you a brief overview of the overall project and give you a welcome. The agenda is very simple. The project overview is for me, then Hette will take you through the main tie-ins. The flue gas tie-in and the steam and condensate are the biggest and probably the most technically interesting. But the electrical supply and cooling water is also important, and MPP3, our power station, is a direct seawater cooled power station, which has a significant impact on the cooling water in the tie-in design. There's also the other interfaces, and we'll give a little flavour on what happens at part load, what happens with the emissions, and what we've learned from the project. The state of play of road, I mean, I expect most of you are familiar with it. It's been around for a while. It was a project that got funding from the European Union back in the end of 2009, so it's been under development for a long time. We did the engineering feed studies for the capture plant and the supplier selection in 2010. Then value engineering and detailed design rolling forward until early 2012, at which point we were very much ready to build, and we had we had chosen the supplier whose floor, we had done a lot of the detailed design. We'd even got orders placed for some of the long lead items like the CO2 compressor. But the project was stalled in the spring of 2010 over lack of funding and low carbon price. We've now reached almost 2 years haggling for more money, because the collapse in the carbon price and delays on other low carbon incentives has meant that the project loses a lot of money. That is still going on. We still have a very live discussion. The current commission is trying to get the project over the finishing line before the European elections. So there's lots of discussion still going on. We've recently been in the news in the Dutch papers, but I can't report any concrete decisions. So the finance problem is still not solved, but we do have all the engineering done. We have all the permits done, or very nearly done, and yeah, we have the contracts ready to go, both on the storage side with TACA and on the capture plant. So we're very well positioned, and the only problem is the usual problem, which is money. and I'm sure that when that is resolved, you will hear about it. There'll be a big fanfare. But I can't give you any good timetable or information on that. But that's basically where we are with the general state of play of the project. We have a little video which I will try and get to work. Here we go. It illustrates the location. So we're in Rotterdam. Rotterdam is Europe's largest port. It has 15% of all the CO2 emissions in the Netherlands, so it's a very big industrial area. We are on the back of a power station which is now commissioning, so it's an existing power station which you can see in white there, in the port very close to the sea. And the capture plant, which is in blue, is located around the stack, around the chimney. And that gives us nice short times for the flue gas, but rather long times for the steam and the condensate. What you can now see as we zoom in are the main columns. So you've got the direct contact cooler, the absorber is the tallest one, and the stripper is the one on the left-hand side surrounded by scaffolding. This is a floor design. We won't go through the details of the capture plant today because we'll be talking about the interfaces to the power station. But that gives you a rough idea of the scale. Probably best if I hand over to Hette now, and he'll take you through the details of the tie-ins and the capture plant.
Okay, thank you very much, Andy. This is Hette speaking from now on. Well, this is just a picture of the Maasvlakte power plant of E.ON. In front, you see the Maasvlakte power plant number 3. That's being built at the moment. It's a 170 megawatt electrical single train unit.
1,070.
Sorry, 1,070. Single train means one boiler, one steam turbine, one generator. It's fired with pulverized coal. The coal comes from all over the world. The efficiency is over 46%. The first synchronization was in 2013, but the commissioning is still continuing in the first half of this year. Well, at the left you see the harbor where the seawater, cooling water comes from, and in the front at the right side you see the cooling water outlet pond. Well, the capture plant, Andy already mentioned that. The technology provider is Fluor. It's a post-combustion type. The capture capacity is 250 megawatt equivalent. That means we treat, in this case, 23.4% of the flue gases that is generated by MPP3, and we treat them in the capture plant. The capture plant in the design point is over 90%. The capture volume we can capture yearly is 1.1 million tons a year. We hope it will be operational in 2017 if the financial issues are solved. The transport goes through a 25 kilometers 16-inch pipeline that's designed for a gas phase transport. And the storage is in a depleted gas reservoir in the North Sea called P18A, and it will be at over 3 kilometers depth. Here you see the combined picture. The boiler of MPP3 produces more than 800 tons per hour of CO2. about 189 tons will be transported to the capture plant. 90% will be captured in this plant. That means 170 tons per hour, and that will be compressed and will be stored in the storage under the North Sea through this 25 kilometers pipeline. On the next slide, you see the composition of the flue gas and also the main process data. The temperature of the flue gas to the capture plant is around 48 degrees. The volume flow amounts to 700,000 cubic meters per hour, and the CO2 content is about 13.7 volume percentage. Here you see the 3D picture of the capture plant. Andy already mentioned the main components. In the middle you see the stack of MPP3. At the right side you see the DCC cooler, the direct contact cooler, where the flue gas is cooled before it enters the absorber. And in front of the stack you see the stripper, and at the far left side the compressor housing. Here you see the full process scheme of the capture plant. It has several interface points with the MPP3 plant. Those are encircled in blue. Well, from left to right, you see the flue gas entering from MPP3. It goes through the DCC cooler, where it's cooled, and on top of this DCC cooler it is desulfurized. Then it enters the absorber column, where it's washed with MEA fluid to absorb the CO2. The treated flue gas leaves the column at the top, and the CO2-rich MEA fluid is pumped to the stripper column. There it's heated with low pressure steam. The CO2 is released there and compressed and transported to the storage. Now we come to the main interfaces. The main interfaces are the flue gas tie-ins, the steam condensate supply to the capture plant, the electrical supply, and the cooling water. With the main interfaces, well, some high investments are involved and rather high operational costs. There were two time-critical interfaces. At first, the flue gas tie-ins, and secondly, the steam and condensate tie-ins. We decided to execute those tie-in works before the commissioning of MPP3 started, because during commercial operation it will be too costly to plan a very long outage to execute those tie-in pieces. The first work that was executed in 2012 were the flue gas tie-ins. The tie-in point can be found inside the concrete stack of MPP3. I will try to point it over here. At 60 meters high in the chimney. There the GRP duct, the flue gas duct, makes a 90 degrees turn, and two nozzles were installed. You can see them at the right side in red. Both 3.8 meters diameter, one for the extraction of flue gas from the power plant, and one for the return of the flue gas. that is treated in the capture plant. Later on, the ducts to and from the capture plant will be connected here and run inside the stack to an opening at the ground level. Now we come to the steam and power supply. The steam and power supply are the main operational cost factors of the capture plant. There's a high steam demand and high electric power demand, and those can give a very high power loss of the MPP3 plant. So we did some research on this. The results of this are shown on this slide. From left to right, at the most left, you see the power figures and the efficiency figures of the MPP3 power plant without CCS. Then to the right, the 3 options with external boilers for a steam supply. The 5th option is extraction of steam from MPP3, and at the most right side also the steam extraction from MPP3, but also with some heat integration. I will come to that later. The last option was the preferred option, although it leads to a reduced power output of MPP3. But we have chosen this option because it has the lowest capital expenditure, the highest efficiency, and it is the least complex one because we don't have to build any extra boilers. Now we zoom into the process flow diagram of this steam solution. On top you see the steam turbine of the power plant. From left to right, a high pressure steam turbine, the medium pressure steam turbine, and the 3 low pressure steam turbines. At full load of MPP3, the steam is extracted, leaving the medium pressure steam turbine. In part loads, the pressure is not high enough for the capture plant. The capture plant is presented in the green box. Therefore, we plan to install a so-called steam jet booster. The driving steam for this steam jet booster comes from the outlet of the high pressure turbine. It will increase the pressure to the desired level. The pressure of the low pressure steam we will extract all the time. Condensate will be pumped back to the condensate system of the power plant. You see at the bottom side of this slide. And furthermore, condensate is used for some cooling of the CO2 leaving the stripper in the capture plant. We also come back to that later. Here you see some pictures of the tie-ins we have made last year in 2013. The right picture is the low pressure extraction point. The 1200 millimeters tie-in piece is installed there, and at the left picture you see the tie-in of the high pressure T pieces. This is a picture I downloaded from the internet of the steam jet booster. In our case, the steam jet booster will be around 50 meters long. At the left side, you see in red where the high pressure steam is injected, and that will boost the pressure of the low pressure steam from 2 to 3 bar to the desired pressure level of over 3 bars. Now we come to the electrical supply. The power plant has a 10 kV auxiliary system that is showed over here. Normally the power of the system comes from 2 auxiliary transformers that are shown at the right side. For emergency situations, the power can also be delivered by 150 kV grid connection and 150 to 10 kV transformer. This transformer will also be used to supply electric power to the capture plant. And when there's an emergency situation at the power plant, the capture plant is switched off and all the power is available for the power plant. The advantage for road was that no extra electrical transformer was needed for the capture plant, and this outweighed some extra grid cost we have because we have normally a power supply from the external grid and not from the power plant itself. Now we come to the cooling water. Here we presented the selected option. The overall cooling demand of the capture plant is more than 200 megawatts, and compressor adds another 20 megawatts to this demand. We evaluated 3 options to make the connection to the MPP3 cooling water system. We have decided not to build a separate cooling water system to avoid high capital expenditures, but we extract cooling water from the supply line to MPP3 and dump it in the discharge pond I've shown on the picture before. Part of the cooling is done by using condensate from the steam system of MPP3, shown at the bottom side of this slide. As said, we use it to cool the CO2 flow from the stripper before it enters the compressor. The cooling load is about 30 megawatt of the stream, and the advantage of cooling with this condensate is first that we have a smaller seawater cooling system, and secondly the heat recovery gives an improved efficiency at the power plant. Here I show the options that are not selected for the. I won't go further into detail of those options. Here you see some pictures of the cooling water connections. The MPP3 cooling water ducts run under the plot of the capture plant, so the connection points are close by. The suction pipe of a booster pump that pumps the seawater through the cooling water system of the capture plant is connected to 2 manholes. There are no changes to the seawater cooling of the power plant, and that is the main advantage of this solution. Now I will shortly mention some other interfaces between the capture plant and the power plant. At first we need some demineralized water at the capture plant, about 10 tons per hour. It comes from an external company, Evides, that also delivers this water to the power plant. Further on, we use the potable, the rain and the sewage water systems of MPP3 for the capture plant. Connection points are also close by. One big waste stream of the capture plant is the flue gas condensate. That this is almost pure water that can be used very well in the power plant for the flue gas desulfurization. So we connect it to the process water tank of MPP3. And this reduces the freshwater intake from the nearby lake significantly. The deep FGD condensate can't be used because it's slightly polluted, but we can dump it in the cooling water. In the cooling water discharge that goes to the outlet pond. Further on, we also use the fighting water system of MPP3 that runs around the plot already. Yeah, some words on the operation and emissions. At first, the operating window of the capture plant that is shown here. MPP3 can run between 25 and 100% of the maximum load of the power plant. And the capture plant can run between 40 and 100% of the designed maximum capacity of the capture plant. That means we can treat between 280,000 and 700,000 normal cubic meters of flue gas per hour. Operation is expected to be take place mostly at the top side of this window. MPP3 is expected to run most of the time at 100% load, and when electrical prices are really high, we can reduce the load of the capture plant to have a more economical operation of this capture plant. In part load of the power plant, we will probably run the capture plant as much as possible in at the full designed flow. The parallel operation will probably only used for demonstration purposes. Yeah, the next slide you see the specific carbon emissions we calculated, the effects of carbon capture and also of co-firing biomass. At the moment we are also engineering co-firing of biomass in the MPP3 power plant. On top you see the specific CO2 emissions of the power plant without CCS or biomass. In orange you see the specific emissions in part load of MPP3, where we will even have lower specific emissions than in full load, because the carbon capture plant can run at full load when MPP3 is in part load. In the bottom lines you see the combined effect on the CO2 emissions of both the CCS plant running and biomass being fired at around 20% of the 20% of the weight percentage of the total fuel flow to the capture plant. Now a few words on the lessons learned. We hope that the solutions we engineered in the road project can also bring up ideas in other CCS projects. Both the capture plant and the interfaces are engineered with low redundancy and low engineering margins to make the CCS as economical as possible. We have made use of existing capacities of the MPP3 systems as much as possible. Well, the first learning point is that heat integration can save both capital expenditure and operational expenditure, because improved efficiency. Secondly, steam jet boosters may be economical for part load power plant situations to ensure enough pressure in the reboiler for the reboiler steam of the capture plant. Well, further heat integration for 100% capture would require external consumers of this low temperature heat, because the condensate system of the capture plant can't take up all the rejected heat. Low temperature district heating would be ideal to supply the waste heat of the capture plant. The condensate retrieved in the direct contact cooler can be used as process water in the power plant and almost eliminate external fresh water supplies when 100% capture would be installed behind the coal-fired power plant. Okay, this was it for today. I hope you have some questions. We will be glad to answer them.
Thank you very much, Hette and Andy. I'm going to press on with the questions, and just a quick reminder, we've got that little box that you'll see on your screen, so please submit them. I'm delighted to say we've got quite a selection of questions, so I'm going to kick straight off and hand to our panel to answer those questions from now on. So first of all, what is Road doing to address the financial gap? Is it still likely to go ahead given the low support levels for CCS in the EU? And look, Andy, I think you probably made your position clear on that, but I'm being the chair and I still have to ask those questions.
Well, we've actually, I mean, we've spoken to all sorts of people. We've explored all sorts of options on the funding position. I don't know whether the project will still go ahead, is the honest answer. We do have some proposals on the table. They do require a larger contribution from external funders. The external funders want a larger contribution from the parent companies, and they are negotiating. The impression that I get is that a decision will come soon, that the project will either go ahead or will stop.
Okay, look,
I can't give a probability.
No. Look, I think we've you've gone as far as you can go with that. But thank you for that. So please explain why the capture rate is only 90%. Says one of our questioners. The 1.1 million tonnes per CO2 captured is less than 25% of the available CO2 emitted.
Okay, the position there is that the capture plant is sized to be the equivalent of 250 megawatts, and that was driven by the grant situation. The EU grant requires 250 megawatt scale. Now, if we made it bigger, it would have cost more and the funding gap would be bigger. So we positioned it at 250 megawatts to minimise the funding gap. The power station itself is 1,070 megawatts, so we only take about 23% of the flue gas from the power station.
Okay.
That's why we get a low percentage of the total power station. We do 90% capture because that's the sort of level that we would need to do on a large scale to be effective against climate change. There's no magic about 90%. The issue is that the higher you push that percentage capture, the bigger the energy penalty. So it costs you more it costs you more in energy and steam use for the extra tonne that you capture if you go much beyond 90%. But certainly I've seen pilot plants running at 92, 93%. 95% is achievable. It's just more expensive. So 90% is the general benchmark that people design to.
Fair enough. So the project appears to have a limited lifetime. If there's a decision to proceed to full capture from the plant, will you be able to use the selected storage sites, or will you require other storage sites?
The physical plant that we're building has a design life of 20 years, although we don't, for most of the plant it's low temperature and low pressure, so it's not particularly got a limited life. The existing storage sink, we didn't talk about storage, but the existing compartment in the P18 reservoir will hold about 7 to 8 million tonnes. So we have to spend some more money to develop a new reservoir after 7 or 8 years. There is P18-2, which holds about 25 million tonnes. We estimate that'll be maybe 30, 40 million to develop that. So not a great expense, and that can be reached from the same platform. There are some other potential depleted gas fields nearby. So for the size of plant that we're building at the moment, there's some incremental investment, but there isn't a big problem with storage. There are also some aquifers further north in the Dutch waters, so if we did get the opportunity to go to the whole power station, there are potential sinks we can use, but they would be a new development.
I think it's a question here for Hette. Is the capture plant described by him in page 7 of the presentation going to be retrofitted for at some point capturing all of the CO2 generated? It seems it only captures now about 20% of produced CO2, so there's a bit of crossover with what's been said before.
Yes, that's right. The capture plant that is designed at the moment can only take up 23% of the flue gases. When we have to go to full capture, we probably have to make a whole new capture plant that is designed to take up 100% of the flue gases.
Yeah. And what's been the criteria used to select the capture technology provider? You know, be they technical or economical?
Yeah, I mean, there was a string of criteria in terms of how well proven it was, what the technical risks were, what the emissions were, how easy it would be to permit, and for some of the more novel solvents that was a potential concern. What the energy penalty was, so the true life cost. In fact, the energy penalty was not that different for the different suppliers we looked at, and it mainly came down to the how well proven it was, how easy it was to permit, and the capital cost.
Okay, and if the CO2 is transported at gas phase, what is the compression ratio of the CO2 compressor discharge pressure?
Yeah, we didn't focus on that because we were thinking about the interfaces, but it was designed for gas phase in terms of the pipeline sizing. As the reservoir fills up, we will go into dense phase, so the compressor will be designed to go up to 100 bar. The inlet pressure, I think, from stripper is about 1.5 bar, and the discharge pressure will increase progressively as the reservoir fills, finishing off at probably just below 100 bar.
Okay, and is the carbon capture unit an amine process or a sodium hydroxide reagent process? Are Road and Floor using a variation of the Benfield process to capture CO2 instead? So what are the options that you've gone for there?
We've gone for, we're using MEA. We're using a conventional amine process for the CO2 capture. There is sodium hydroxide used for the sulfate polisher.
Okay.
So we make sodium sulfate.
And is the parasitic load for CCS around 55% of the power plant capacity?
Parasitic load for CCS is nothing like 55%.
No, it's around 6% of the power output of MPP3 for this part load capture plant.
Okay, and related, do the efficiency figures include energy for CO2 compression?
Yes, they also include energy for the CO2 compression. The CO2 compressor takes about 50% of the electric load.
Okay. And would the total efficiency be reduced to about 30%, says another questioner, if you built a full-scale capture plant which would process 100% of the flue gas?
Yeah, well, our calculation, if we use this system of steam extraction for a full scale, it would come up to about 34% efficiency for the whole power plant, including 100% capture.
Right. And how much or will any condensate need to be disposed of and where?
Well, 100% condensate, we could use most of it in the MPP3 power plant because we need quite some amount of fresh water. But well, the water we can't use there could simply be dumped in the cooling water outlet pond because there's hardly any contamination in it.
And then we've got a lot of questions about the percentage load. Is it likely for the plant to run at less than 40% load? How does that impact on the overall business case for a coal-fired power station?
We don't know exactly how low. MPP3 is still in commissioning. It was a design criteria of the boiler that it could go down to 25% load. I've never actually seen a coal power station regularly operating at 25% load. So it remains to be seen what it actually does in practice once it's commissioned. The issue, I mean, it won't operate for very long periods at very low load because it's cheaper to turn it off and back on again. So you're just talking about periods overnight when there's a dip in power prices where you run at half load in order to avoid coming off. The capture plant we know will be able to run at full load with the power plant going down to 40% load. If the power plant's below 40% load, we start to struggle with the steam supply. Yeah, we will have to test it and commission and see what we can do when the plant's operation below 40% load. I mean, I can't really comment in too much detail about the business case for coal power stations. If you've followed the news about the European energy markets, the business for any power station is looking very bad at the moment. We have gas power stations that have been built and not commissioned in the Netherlands, at least one. E.ON is doing so. Neither coal nor gas power stations are actually making very much money at the moment.
Sure, so that's an interesting the context that you're operating in. So what's the phase of CO2 at the injection site? There are only 3 CO2 compressors after the capture plant. Is there additional compression at the injection site?
No, there's one CO2 compressor at the power plant. There is no CO2 compression at the well.
It's a 6-stage compression. So the 8 stage.
It's an 8-stage compressor, but there's just the one compressor house that takes it. So the compressor takes all the CO2 that is captured and puts it in the pipe. And as designed, the pipeline pressure basically floats according to the reservoir pressure. We have an insulated pipeline, so the CO2 goes into the pipeline warm, so we don't fully cool it as it comes out of the compressor. And that means that the pipeline should stay in single phase. because it stays above the critical temperature. But the pipeline pressure then floats, and if the pressure at the well is not high enough, then you don't get enough flow, and then the pipeline pressure goes up until you do get enough flow. Yeah.
Okay, we've got quite a few questions here, so I'm rattling on a little. What kind of filter system is considered to be used for seawater in order to reduce fouling in the coolers?
Well, there's filtering at the inlet, at the cooling water pumps. I don't know all the details of this filtering system. And we will also have a mussel filter at before the cooling water ends the cooling water system of the capture plant.
Okay. And what's the net efficiency of the power plant, allowing for the power required for cooling and compression?
Can you repeat this question?
Yes. The question is, what is the net efficiency of the power plant, allowing for the power required for cooling and compression?
Yeah. 3%.
Yeah. 44%.
Okay.
It's around 44% when the capture plant is running at full load.
Yeah. And a sort of related question, for a baseload plant, the load penalty of 40 megawatts costed at, say, 20 megawatts an hour means $800 per hour without even considering reduced efficiency. Any comments on that? It seems a very large cost.
Well, both steam and electricity supplied to the capture plant are very costly, and one of the main, the main operational cost factors.
Yep.
Yeah, you need just to come in on that. I mean, you need a significant price of carbon to make this work. You need a clear penalty for your CO2 emissions, which at the moment we don't have. We have a carbon price of around €5 a tonne. Our rule of thumb is we've got a conversion for the steam penalty into electricity lost in terms of lost generation from the power plant, and if you combine that with the works power for the capture plant and the compressor, it costs you about 1/3 of a megawatt hour for every tonne of carbon you capture. So about 1/3 of a megawatt hour for every tonne of carbon. So that means if your electricity price is 60 euros a megawatt hour, you need a carbon price at least 1/3 of that. You need a carbon price of 20 euros a tonne, purely to pay for your lost electricity and your steam demand.
Yeah. Okay.
And so it is a substantial cost.
Heating integration of CCS and power stations is a trade-off between capital and operating expenses. Were there further opportunities for heat integration that were eventually ruled out? Any techniques used to assess the best heat integration opportunities, for example, pinch analysis or others?
Well, we also reviewed this heat integration with Hylkema. They also came to the conclusion that this was about the maximum economical heat integration we could achieve. Just heating the main condensate with part of the rejected heat of the capture plant.
Okay. And what is the capex and the opex for the 250 megawatt capacity? About €1 billion or 1.35 US billion?
We're talking about, for the capital cost, we're talking for the whole project, so that's not just the capture, that's transport and storage and everything. We're talking about a little bit less than 500 million euros.
Okay. Okay.
The operating cost it depends on how long you run it for.
Of course.
But the largest operating cost is the lost electrical generation, or plus the power consumed, the electrical penalty.
Good. Look, we're pretty much running out of time for further questions, but I'll just ask you one more. Did the upstream flue gas treatment include specifics that were required only by the capture plant?
No. No, it's a slightly unusual configuration because it's a wet stack, which is why we have cool flue gas in the stack at the elbow. But no, it's a conventional plant, and it was designed to be an efficient coal plant as it was, and we have taken the flue gas as it comes. It does have fairly good modern emission standards. The level of particulate and sulfur and NOx are all very low, but we still required additional sulfur polishing.
Okay, and look, the last question I think we can just squeeze in. Between using low P steam and steam jet booster together and using moderate P steam and make it saturated, why do you choose the first option, that is using low P steam and steam jet booster?
Yeah, one of the reasons was that we in part load were not able to take so much medium pressure or high pressure steam from the power plant. With this steam jet booster, we can avoid it and still run the capture plant full load during part load operation of the power plant.
Can I add a couple more reasons there?
Please do, yeah.
We want to use the low pressure steam at full load because that's the most efficient, and we expect the power plant to be running most of the time at full load. The other point about the steam jet booster is controllability. So when you turn down, if you only have a low pressure tie-in and a medium pressure tie-in, at some point you have to switch, and you have an abrupt transition. If you have a steam jet booster, you can gradually turn up the medium pressure steam as the low pressure steam pressure drops with load. So it gives you a smooth transition and good control.
Okay. Look, I think we've got 95% of the questions, but on behalf of our audience, I'd certainly like to thank you, Hette and Andy, for taking those questions. If there are any more questions, and we'll pick the ones up that haven't been answered tonight, please do submit them to us, because we'd be delighted to pass them on and get you an answer. So I would encourage you to do that. As I mentioned before, the recorded webinar and the slides will be on our website in a couple of days' time. So on your behalf, I'd like to thank Dr. Andy Reid and Hette Hylkema for giving this presentation tonight. I'm sure that you understand that we have to squeeze this into an hour, and that's always a challenge. I would like to say that we would always welcome your feedback on this webinar, part of the process of making these as good as they possibly can be, and also on other topics. We try to cover the whole CCS chain with a range of webinars, and we're very interested in sharing expertise across that. So if you have ideas for topics, please submit them. My colleagues suggested that as of January, there's an excellent new report on our website, the Road Integration Report. Feedback we've had just in the last couple of weeks that it's well worth looking at. So that's on the website now and a recommended read. So I would suggest you take a look at that. So we're going to close the webinar tonight, and I'd like to thank our panelists again, and also the Road Project, of course, and all of you for participating and certainly keeping us going with some excellent questions. And I hope you've enjoyed it, and thanks again. Thank you very much.
Okay, thank you.
Thank you.
Good morning, good evening.
Good evening and good morning to you.